Hello, welcome to another problem session. So today we're gonna tackle a problem in the definition of work. Okay, so you probably know this. The definition of work is if an object is moving and so in this direction it's moving and goes from here to here, let's call that delta r vector displacement. This is a displacement, and there's a force acting on it. Other forces may be acting on it, but the W by F, so it's called a W by this F, is F dot delta R. And if it's like from here to here, from point A to some point B, so this has to be done at infinitesimally. So W A to B is integral on this path. So there's some way to describe this path. It may be like x is constant, y is constant, x equals to y, some path here, and so this becomes a this kind of integral, and integral is over path on path from A to B. So this is integral. So if f is constant, so this becomes simple. If f constant, then it's just f d cosine theta. So from here to here, that's the vector. So this is A and this is B, and f is this way, and this is theta, and from here to here is d. If f is constant. So if f is constant, this integral is very easy and it becomes like that. And many times that's the case, but if f is not constant, you have to do integral. Now this is an example. In this example, the force is not constant, it's a position dependent. So it's for instance, over here, if you look at it, if I'm over here, y is 0, so the force is that way over here, perpendicular to that. When I'm over here, x is 1, but y is varying, so over here is something like that. So that's the f over here, and of course over here is f is that way over here. So for instance, when you take a half, say at the half point mark, if I look at over here, this 1 over half here, and this will be half. So it's kind of actually is the same direction here. But if I go someplace else, it's another direction. So okay, so that's the case. And so there are two parts, and in this part there is subpart phi on OA, phi on AB, and phi on OB. Okay, so I'm going to do this out one by one. So say on OA, I see that we have a y equal to 0, and x goes from 0 to 1. So this is the path. So this is a description of the path. And what is f dot dr? This is in the for every path. So f dot dr is the paths. I'm going to get the formula. So this is a dot product, and f is like that in I and j hat. So I would like to know what the dr is in I hat, just so I can take dot product. So dr in general is I hat dx plus j hat dy plus k hat dz. And this I hat is j hat, k hat are unit vectors. This is along the positive x-axis, and this is along the positive y-axis, and this along the positive z-axis. Positive z-axis. Okay, so if I take a dot product, I get y I hat plus 2x squared j hat I hat dx plus j hat dy, and this goes with that, so get a y dx plus 2x squared dy. Okay, so if I look at this, and I'm going to do, because this is changing, I will think in terms of this integral. So W OA will be this integral of this thing on this path. So y equal to 0 and x goes from 0 to 1 of this quantity y dx plus 2x squared dy. So you could see when y is 0, so this goes away, so this makes it 0, and here dy is not changing, y is fixed, means dy is 0, so this actually is simply 0. And you can tell from here, so on this path you're going this way, but the force is pointed 90 degrees. So if you're thinking in terms of angle cosine 90 degrees will be 0. So this is consistent, so this is correct. So let's look at the other part. I'm going to go from A to B, and that path is, of course, f dot dr is the same. F dot dr is still y dx plus 2x squared dy, but path is x equal to 1 and y goes from 0 to 1 on this path. So just on the path x equal to 1, so I put x equal to 1, and this means dx equal to 0. X is not changing on the path, so this is 0, but this one is 2 dy. So now if I do the integral, and it goes from 0 to 1 on this path, 0 to 1 2 dy, so it's like 2. So W work A to B is this. Okay, let's do the third one. If I go from here to here in that path, on this path is, on this path I have y equals to x. So when I look at FDR, it's still the same, but I don't have independent, x and y not independent, they're related like this. That means I can write f dot dr, simplify it, x dx becomes, and then 2x squared dx. So I can write everything. This means dy equals dx. So I can write everything as dx. So this is an integral in x only, dx, and on that path x varies from 0 to 1 on that path, and x, so is this the case, and x varies from 0 to 1. I could have done y varies from 0 to 1, it will be exactly the same thing. Integrate f dot dr on A to B direct path, and that's a x plus 2x square dx, and go from 0 to 1. This is x squared over 2 plus 2x cubed over 3, 0 to 1 is half plus 2/3, and that's equal to 6, and 3 plus 4 is 7, 7, 6. So that's the answer for this, and that's the answer over here. Okay, so boxing up the answers. All right, so we got this, this, and this. You notice that if I go from O to A and A to B, so if I go from O to B, but I go on this path, let's call it path 1, and this one is path 2, I don't get the same amount of work. So WOA plus WAB is not equal to WOB. All right, so that's a notice that. Okay, now when I look at this, this is 1. Oh, I numbered them wrong. This is 1, 2, and this is 1, 1C, and the other one is 2. So let me do that one out. It says, what is the work done on a closed path? I go this way, but I return, not go this way, but backward. If you look at this calculation, when I go backward, I go from 1 to 0s instead of 0 to 1. So this is the same, but I get 1 to 0, which might get a negative of that, right? So this will be for 2, part 2 is WOA plus WAB plus WBO, and this one was WOB. So this will be negative relationship. This is 0 plus 2, and this is negative 7, 6. So 12 minus 7 is 5, 6. So actually I all the way went around, but the network, I came back simple as the network is not 0. So W cycle is not necessarily 0. Now if you had a constant force, you will see that the whole thing will turn out to be 0. You also see that forces like conservative forces, like gravity, spring force, and in general, when you have a conservative force, this will be the case. There's like if you have a non-conservative force, such as friction force, in general, for friction force, this kind of situation will happen. Of course, for friction force, the work will be negative because the force will be actually taking the energy away from the system. This force is the way it's given. This force actually putting energy in the system, and that's how the work is positive. Okay, I hope this clarifies some of the little steps we do when we compute work by a force. So just to recap, first thing to notice is we really need to know the definition. Fundamental definition is this. Now when we have a not just small path on which we can think of as constant, and this is a dot product, but if I have a large path, then I need to collect those little things on small segments of the path, and then that means I'll need to do an integral, and this integral is quite difficult in a way because it's easy to make a mistake, and that's why I kind of work out more detail what you would need to do in order to do such integral. Okay, so you really need to separate it out and use the information about the path and the force function dependency. However, if force was constant, then you can just this thing simplifies to FD cosine theta. I would never, a lot of students memorize FD. I don't know, FD is wrong unless they're in the same direction, unless cosine theta is 1. If the displacement is this way, if the D is that way and the force is that way, then you'll have cosine theta will be minus 1. So cosine theta will be minus 1. If the D is that way and the force is also that way, then cosine theta will be 1. So if you have memorized formula FD, you got to know that that's just a special case. In general, it should be FD cosine theta for constant force. If the force is not constant, you got to do the integral, okay? And you got to pretty much proceed the way I have done in this exercise. Hope to see you in another video. Don't forget to subscribe. Okay, see you, bye.